All right, welcome everybody to week 5, day 1. I just revealed everyone's IP address, so starting over real fast. The main learning point for today so far is that if you have a class named Bob that takes a template parameter, template class t int size, then size has to be determinable at compile time. So if you have int main like this, you can do this, Bob int 2000, name Bob, that works fine. But if you had like int x equals read, that will not work because you cannot tell what x is at compile time. And even if you slap a const onto here, it doesn't help. Okay. You have to make it a Constexpr. That's the first learning point for today. Constexpr keyword. And Constexpr means you can determine what it is at compile time. Okay. So, is my caps lock? Okay. So this will work, but determinable at compile time, not runtime. And there is also Constexpr if. So if Constexpr x is less than 3000, see out high, else see out high. Normally an if statement is going to insert code for both branches. It's going to emit the assembly code for both the high branch and the by branch. When the code runs, it comes in and says which one is which. And if Constexpr won't. And if Constexpr, this if statement runs in the compiler, and the compiler only emits code for the branch that runs. So this branch here won't appear anywhere in your output, ever. You know, because x is 2000. Right? And so using if Constexpr, you can eliminate an if, and you can also just excise giant blocks of your code. We used to do that using something called like ifdef, Linux, you know, something like that. Then do one thing, else do another thing. This is the C way of doing that. The C way is by using the preprocessor. The preprocessor would check to see if some variable is set in the preprocessor. For example, we could define g libc have linux random h. Probably shouldn't do. Let's say define csci is awesome. And then this whole thing here, these 5 lines of code, will be replaced with just this one line of code here. See how high? Because csci is awesome is defined. Okay, so you could have different blocks of code. I think Aaron was asking about this a while back. You can have different blocks of code for Linux and for Windows, right? So you can selectively add in parts of your code with one hashtag define and pull it out and put in other blocks of code with the other one. And if Constexpr is the C++y way of doing that. Okay. Second thing we talked about is refactoring code. Making your code the same but different. Okay. So if we have this thing here, it's a compile time parameter, and we had, let's say, array, array int size size. If you had this before, this won't work if you're going to be reading in the size as a command line parameter. Okay. If you are going to be using argc and argv, then it must be a constructor parameter. So you have to refactor it so it's not in the template parameter anymore. Constant size, and then we're going to be taking new size, and we're going to initialize size to be new size, like that. Can't use an array anymore. Array has to be compile time determinable, so we use the vector events instead. And we will simply vec.resize to be new size. And then all of your code that uses size will have size set here. Even though it's a constant, it still can be set. Constants can only be set in the initializer list like this. Okay, so, and then we come down here and refactor that. So rather than passing in x as a template parameter, we pass it in as a constructor parameter. And now we can do, rather than having it be a constant expression, we can say it's equal to string to integer of argv 1. And it's always good practice to check your arg count. And we typically write a function called usage, cout, enter the size of the can't do if Constexpr anymore because x is no longer a compile time determinable thing. Just get rid of all that, and this is probably a good starting place for you to work on your hash table if you didn't already. When you do inheritance off things, if somebody declares a virtual function, so if you inherit off of Bob, one more learning point for today is the override keyword. You put it after the function signature, and it means I must override a virtual function. So if I say Alex void talk override like that, override like that. See how I am Alex. Then everything works fine. This is overriding a virtual function. If, however, I say I'm going to be overriding talk2, oops, shoot, see. I guess it's, why is it not? Ah, whatever. That's what override's for. So it ensures that you are overriding something on the boss. Did that compile? No. Good. Okay, it's enough of that. You have a week from today to do your last chance on it. All right, so let's move on to counting. Hopefully you all learned some computer science from that. That's one of the reasons why I do computer science in this class, because there's a lot of stuff, and you need to just keep learning, keep pushing yourself. Okay, so big topic for today is lists. Actually, let's take a break. This seems like a good spot for a break. So let's come back in 10 minutes, 10:50, and we will continue with sets, or lists versus sets then. Okay. All right, welcome back. So I was going through some of your hash table reports. Some of them were good. Some of them were not good. So essentially just due to the amount of time it takes to do them. So let's pull up Gregorian's. This is a good one here. After writing the code for double hashing is faster. By the way, a lot of you got different results, and kind of depends on your implementation, I suppose. So a little bit of analysis, and then he's got the running time graphed out with the different sizes and the different loads. So this is how he graphed it. Other people flip the axes around and things like that, and that's fine too. So you can see here linear probing has this kind of hockey graph stick at 90% load, or up to 99% load, and yeah, it's a worst case runtime of 8 seconds. Chaining, the worst case runtime is 4 seconds, so chaining is a lot more consistent, I suppose, in his implementation. And then double hashing, worst case is only 3.5 seconds, which is even faster than chaining. It's a bit odd, but there you go. So that's his data, and his analysis makes sense from that perspective. So yeah, I got through, where was I? About L or M in the last name. So I got about half them graded during the break. I'll get the rest done after this. So let's talk about stuff. Let's talk about math. Let's talk about lists. And you all should know this already. You've done these iBooks, but it's still worth me going over. The main difference between a list and a set is that they're both similar in that they're things can be in a list, or things can be in a set, or not in it. But a list has order. So, for example, if you go to a line at a movie theater, back before there was a pandemic, people would all be sitting in line, right? And the teller would call forward the first person from the line, right? That's a list. Everybody is in order. Whereas a mob of people all standing around chaotically, that would be a set, right? You're either in the mob or you're not in the mob. With a list, you can either be in the queue to line up for the tickets or not in the queue, but also I'm third in line, or I'm fifth in line, or I'm seventh in line, okay? And so a line that has me first in line is a different one from me being last in line. Like that's a distinct, different list, okay? So if I've got 3 students from game development standing in line, there's 6 ways I can do it. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, 3, 1, 2. So there's 3 possibilities for the first option here. And then after the first person is in the line, there's 2 people left that you can pick from. So there's 2 options for the second one. And then after you've got the first 2 people in line, there's only 1 person left. So there's 1 option for the last one. And the total number of possibilities would be 3 times 2 times 1. Or factorial. All right. So, yeah, it's really important to understand the difference between lists and sets, especially when I'm asking for like how many are possible, right? If you've got 3 students, how many sets are possible, right? Person 1 is in or out, person 2 is in or out, person 3 is in or out, versus lists where you can also rearrange them in different ways. Okay. So Factorial, the way that math people scream at each other in Factorial, means that you multiply all the numbers from 1 to n together, right? So 5 factorial is 5 times 4 times 3 times 2 times 1. And this is a sequence that grows very, very quickly, right? So factorial will overflow an integer like by the time you get into the teens, right? You cannot do factorial at very large numbers at all very quickly. Okay, so the anytime you do factorials with large numbers, there's usually going to be a division in there somewhere, right? Like 10 factorial divided by 5 factorial or something like that, and that helps constrain the exponential size of it. Although sometimes not. So sometimes you just get really, really big numbers, like when you're dealing with I don't know how many ways could you put all the people on Earth in a line, right? It's like 7 billion or something like that, right? So it's going to be 7 billion factorial, which is some unimaginably giant number. 7 billion times 699 billion times all the way down. So yeah. So if you're going to be putting people into a line and you got 10 people, the number of ways you can put them in line is 10 factorial, because there's 10 options for the first person, and then after you've pulled one person out of the same person can't be in the line multiple times, right? So now there's 9 people remaining. Okay, you're second. All right, there's 8 people left. You're so there's 9 times 8 times 7 times 6 different ways of putting 10 people into a line. There's 10 factorial ways of putting 10 people into a line. I eat more pies than you. I can eat 6. There's no way you can eat 720 pies. What bad humor. Okay, so so first of all, do you guys understand this? So like if I were to ask you how many ways could you put 20 students into a line, could you tell me what the answer is? If I've got a class of 20 students, I'm going to line you all up. How many different ways could I line you up? Okay, so if I were to ask you how many different ways could you put the 20 students in line in this class, what would your answer be? We got 20-ish students in this class right now. How many different ways could we line them up? 20! Yeah, exactly. Good. 20-ish factorial, yeah, whatever the number is, I haven't counted. Somewhere around there. Okay, so yeah, that's a pretty easy thing. And this whole field, by the way, is called Combinatorics, which is, there's different names for it, as everything is, but basically the number of different combinations and things like that you can make of stuff. It's really important in computer science. It's one of those math skills that every computer scientist has to know at least the basics of, because it comes up all the time, right? Like the most obvious example is passwords, right? Like how many different passwords are possible? If you have a system that limits your password length to 13, and there's 26 lowercase letters and 26 uppercase letters and 10 numbers and 10 symbols or something like that, a few more than that, 18 symbols, something like that. So you have 52, 62, 72, 80, about 90 possible characters, somewhere in that range. So let's say you have 90 different characters on your keyboard, and just to make the numbers even, let's say that the maximum password length is 10. How many possible passwords are there? What do you think? Zybucks was getting into it. Yeah. Factorial of 20 is, a large number. 90 choose 10? Is it? We're not, it's a good guess. It's a good guess. We haven't gotten to choose yet, though. 9? There's 9 different passwords possible. You got 90 possible symbols you can enter. Maximum password length of 10. Let's just say the password length must be 10 just to make life easier on us. At least 6. Right? So there's 90 possibilities for the first key that you hit. And then there's 90 possibilities for the second key you hit. It's not factorial. It'd be factorial if you can't reuse the same character twice. Right? So if you couldn't use the same character twice, it'd be 90 times 89 times 87. But you can certainly hit as your password if you want. So it'd be 90 times 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 90. Boom. There you go. 90 to the 10th power. So that's the difference between, so you have to kind of like pay attention to like the problem, right? Like every time, like if you put somebody first in line, they're not available to be put second in line. You know what I mean? And so if there are 90 people waiting in line, then you pull one person out, you're first, there's 89 people remaining. All right, you're second, so it's 90 times 89 times 8, right? Whereas with the password, you don't run out of the letter A's, you know what I mean? So it's 90 times 90 times 90. And so you have to kind of like be like, all right, do things come back? Can I use the thing a second time? Does order matter? Does order not matter? Like with a password, does the order matter? Does it matter what order I type my letters in? Like if I type in apple as my password, would it work with a LEAP? L-E-A-P-P? Would that work? Does order matter or does order not matter? What do you guys think? Exponents are involved, yeah. Quite big exponents oftentimes. Does it matter what order you type the keys in? When putting your password, yeah, order does. Order does matter. It'd be very odd if you could type in LEAP and have it accept your password. So order matters, right? And so, like mentally, you just sort of have to like be like, all right, okay, we got order matters, and the thing can't come back once we've chosen it. We can't put it back, and so there's kind of a series of criteria you sort of train your brain on. And this intuition is really important in computer science because it's not just passwords and RSA and all that kind of stuff, but like just to develop like a intuition for how long your program is going to run. Like if you're going to be writing like a chess program or something, right? How many possible moves are available the first move of chess? All right, there's 8 pawns, and the pawns can move 1 or 2. 16 possibilities, and then the knights can move, and there's 2 possibilities for knights. That's 20. There's only 20 possible moves. First move chess. Okay, and the other person can respond with 20 moves, and so just for the first 2 moves of chess, there's 400 board states possible. And then after that, you start opening up the board, and the bishop can move, or the king can move if you wanted to on the second move, possibly. And so you sort of start developing a sensibility for like, all right, how hard would it be for me to just brute force try all possible moves for the next 4 moves, right? I'm just going to exhaustively search for checkmate. Every single spot a bishop can be on, every spot their rook could move times 4 times. And you go, wow, that's actually really painful. Like it starts getting really bad because pawns can only move 1 or 2, but like a bishop might have like a dozen different spots it can move to, and then every other piece on their board that can move might have, a dozen spots it can move to. And that's just for one of the pieces. And so you have all the pieces and all the spots they can move to, and all their pieces and all the spots they can move to, times all your pieces and all the spots they can move to, times all their pieces and the spots they can move to. Even with just like 4 like 2 exchanges or 4 moves ahead, me, you, like that can actually get into like, a fairly large number, right? And then let alone like talking about 10 moves ahead or 20 moves ahead or whatever. And so when you develop a understanding of combinatorics and a sensibility for it, then you're like, let's not do that. Let's see if we can figure out like something that won't involve us waiting to the heat death of the universe. Okay. You spent the weekend watching The Queen's Gambit. Yeah, I kind of liked it. I didn't like the whole drug use, element of it. Though. It seemed a little much. Okay, so then you don't always queue up everybody in a line using the entire group. For example, if I wanted to make a line of 3 students from a list of 30, there's 30 possibilities for the first student in line. There's 29 remaining for the second one. There's 28 remaining for the third one, and we're done. So it'd just be 28 times 29 times 30. And so the formula for that is, in factorial, is the size of the class. So it's 30 factorial divided by n minus k. So in this case, it would be 30 factorial divided by 27 factorial. Like I said, a lot of the times when you're working with factorials, a lot of the factorial terms cancel out, giving you some sort of reasonable number. And so a lot of times you'll use big int libraries that can do that. So you don't have to compute a factorial and get this giant number and then divide it by this other giant number. Instead, you can do this, right? And it'll compute it for you in a reasonable amount of time. So 30 factorial divided by 27 factorial is 30 times 29 times 28, right? Sketch it out, I guess. 30 times 29 times 28 times 27 times 26 ... divided by 27 times 26 times ... cancel, 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 cancel. 30 times 29 times 28. Okay. So that is lists. Any questions about this? I know you went over it on your Zybooks, so you probably know this all already, but it's still probably worth going over. It's good. All right. So for sets, so for example, if I had to select groups of 2 students, now we're getting to McCohen's favorite, I think. If I just am going to select a group of 2 students to represent me on the student council or something, there's no first student or second student. Order doesn't matter. I'm just going to pick 2 students from the 30 and send them off to a college council or whatever. Okay. So you're either on the committee or you're not on the committee. So it's a set, right? And there's pretty much always less ways of making sets than there are of lists because there's no ordering, right? It doesn't matter. There's not like A's first and B's second. Doesn't matter. You're either picked or you're not picked. Okay. So I've got 30 students for the first spot and I got 29 students for the second spot. But it's not going to give me the same number. I shouldn't be getting the same number because A and B and A are the same in this case. So you have to divide by the number of duplicates you can get. Okay, so A and B and A are the same. So 1, 2, there's 2 different duplicates. A and C, C and A, they're the same. And so you have to divide by the number of duplicates. And the number of duplicates is actually the factorial, okay, of the size of the committee, right? So if we have 3 students on the committee, we can pick A, B, and C, which is the same as C, B, and A, which is the same as C, A, and B, which is the same as C, B, and A, which is the same as A, C, and B, which is the same as B, C, and A, which is the same as B, A, C. So there's 6 different duplicates when you have 3, right? And so it's just the factorial. So the number of ways I can make a committee of students is just the number of ways I can make a list divided by the duplicates. ABC, CBA, BAC, they're all the same. Okay. So you just take the same the same equation we had before for computing how many different ways we can make a list of 3 students from a class of 30, and we divide by the number of duplicates. The number of duplicates in that case would be 6. 3 factorial. The size of the committee is 3, so 3 factorial. Okay. Makes sense? So if I had a class of 10 and I'm trying to make a committee of size 4 on it, how many different ways can I do that? And we write it like this. So I have 10 people in the class and I'm choosing 4 of them for the committee. So we call it n choose k. We write it with these giant parenthesis signs, and it looks kind of weird because it's math. So it is. But what is 10 choose 4? So we've got 10 students in class. I'm going to pick 4 of them to serve as my representatives at some conference. How many different ways can I do that? The answer is 10 choose 4. And oftentimes in computer science, we'll actually just give that as our answer. Everybody in computer science who's taking discrete math, which is anybody who's anybody, right? Everybody understands what 10 choose 4 means. And so you could write it out as like, whatever. But a lot of times in papers and stuff like that, we'll just say, oh, there's 70 choose 50 possibilities or whatever, and you just write it like that with the little parentheses and everything. So what is 10 choose 4? Anyone? So it's 10 factorial divided by 4 factorial and times 6 factorial. Okay. Easy way of doing it. 10 choose 4. 210. Yeah, Google will actually compute it for you. Dr. Joe will compute it for you. Just Google it. There you go. That's how common it is. Yeah, the equation is the number of ways you can make a list. Like if I was picking president, vice president, secretary, and treasurer for the ACM, then ordering matters. You know what I mean? Because Sarah as president and Shahab as vice president is different from the other way around, right? But if I'm just picking representatives to serve on a committee, order doesn't matter. So to compute the number of sets, you take the number of lists and you divide by the number of duplicates. And the number of duplicates you have is the size of the committee, right? So if you have 4 people on the committee, the number of duplicates is 4 factorial, or 24. So you have to divide by 24. So like I said, the number of sets you're going to get is always going to be less than the number of lists, except when you have 0, 1. Yeah, it's 10 factorial divided by 4 factorial times 6 factorial. And one of the cool things about this is if you actually graph this, you get Pascal's triangle. Have you guys ever seen Pascal's triangle? Is it in the Xi books? Does it talk about Pascal's triangle in the Xi books? Can't recall. You remember seeing it? All right, cool. All right, so if I make a list of 3 students from a class of 30, I can do Lee, Nick, Naji. These are former students again. Naji, Lee, Nick, right? These are all different because I'm putting them in order. If I do a set, it doesn't matter. It doesn't matter how I write the set, by the way. Normally we'll like alphabetize it maybe. I don't know. It doesn't really matter. And so you have to eliminate all the duplicates, right? So there's six duplicates when you have a group of 3 people. Okay, so another word for lists is permutations, right? So there are permutation functions in the standard library, for example, that'll permute things for you and stuff like that. So yeah, if you want to convert between lists and sets, you just divide by the number of duplicates. So yeah, we say in choose case. So if you have 10 people in class, and I'm going to make a committee of 4 of them, you say 10 choose 4. So I don't know why math always uses these like jugs filled with marbles. Like, I've never understood that analogy. Like, I've got a drawer that has socks in it, and I've got 10 socks in my drawer. How many different ways can I draw a pair of socks? Doesn't give me enough information. I'm sorry. Are all of my socks different colors? Are they labeled A, B, C, D? Like, if so, then I'm doing 10 choose 2. If they're all white socks, there's one way. I get 2 white socks. That's it. They don't matter. There's no difference between them. Like, it baffles me, like, when, like, it's always that. Like, I don't know if you guys have taken probability or statistics, but it's always like, there's this giant urn filled with marbles, and you reach in, you take a marble out, and you either replace it or you throw it away, or you have a drawer full of socks. Those are the only 2 metaphors like they ever use, you know. And how many different ways can I make a pair of socks using, if I've got 4 white socks and 5 black socks and 3 green socks? Like, how many different ways can I make a pair? And it's just like the analogies are just so improbable. Use pizza, dude. Come on. Jimmy has 100,000 watermelons in his basement. How many lemons? Like, in each reference, they're always asking how many possibilities. Yeah, but I think it's because they're easy to visualize. I don't know. I have trouble visualizing a giant urn filled with marbles. I don't know. Like, there's 500 white ones and 500 black ones. You take one out. You know, what are the odds you get the same color? You know, you're like, okay, it'd be, 499 or what is it? You know, I don't know. So here's a better one. So Domino's Pizza has 24 toppings available for its pizza. When I made this slide, I actually counted, and you can pick 3 of them for a 3-topping pizza. Let's say there's a coupon. You choose it. You get half off a 3-topping pizza. How many different 3-topping pizzas are possible with 24 toppings available? So the first question is, does order matter? Does it matter if you pick a pepperoni sausage and bell pepper pizza or a bell pepper sausage and pepperoni pizza? Does it matter which order you click the toppings on the website? What do you think? If you pick extra cheese first, then pepperoni, do you get a different pizza than if you pick pepperoni, then extra cheese? What do you think? Yeah, I don't think it matters. Right. Order does not matter. So, actually, with extra cheese, you actually pick that on the previous screen. So let's say Asiago. All right. So when you're on the toppings page, Asiago and pepperoni are on the same screen. It doesn't matter which one you pick first. All right. So yeah, good point though. Good point. Extra cheese is actually on the previous screen. Okay. So let's say you've got 24 toppings and you're going to choose 3 of them. How many different pizzas are possible? Who puts pineapple on pizza? You know, I don't understand the hate for pineapple on pizza, man. Live and let live. So the answer is just 24, choose 3. So there's 2,024 possible pizzas you can order from Domino's. Yeah. It's like, there's a lot of things you can get upset about in the world, you know. Like Tahoe's on fire, you know. I don't know. Pineapple on a pizza, just... Or, you know, getting mad at people that like pumpkin spice. It's like, whatever, you know. I don't know. So much tragedy in the world. It just seems like a very odd thing to be upset about. I wanted to see everyone's reaction to the comment. I'd rather pineapples than sardines. Yeah, I used to think that too. But sardines are like... they're there to give you salt, I think. Like, sardines are basically little bundles of salt and protein. And, I don't know, like maybe if you're like salt deficient, you should eat sardine pizza or something. I don't know. Okay, so if you've got a jug with 10 different colored marbles in it, you're going to draw out 4 different marbles. There's 10 choose 4 ways, assuming the order doesn't matter. Right? If you like put them in order, like the first one's black, second one's red, third one's, then that's different. But if you're just like, okay, I've got these 4, yellow, red, green, blue, then that's 10 choose 4. Cloudy with a chance of meatballs. It's funny. And so you can compute this by hand if you want. I would recommend just using Google. it's faster, honestly. So 24 choose 3, which is 2024. Coming up soon, 3 years from now, it'll be 2024. The year of the number of pizzas. Domino's. Then they add like one more. Okay, so a list or a permutation is when order matters, right? If you're going to be like ordering books on a bookshelf, then order matters, right? Because you're like, a set or combination is when order doesn't matter. Like how many, like I'm going to take 3 books with me on a backpacking trip. I've got 24 books up on my bookshelf. I'm going to take 3 of them. How many different ways can I take 3 books from my bookshelf? They all go in my backpack. It doesn't matter. Order doesn't matter. So that'd be 24 choose 3, right? Whereas, let's just ask you, how many different ways are there of ordering 24 books on a bookshelf? Assuming you're not like alphabetizing it. Like you just kind of put them up there. What do you think? How many different ways are there of ordering 24 books on a bookshelf? By color? By size? What do you think? Yeah, you're right. 24 scream. Okay. Yeah. That's it. There's 24, like you've got 24 books. There's 24 you can put in the first slot. There's now 23 remaining for the second slot, 22 remaining for the third slot. So it's 24 times 23 times 22. If I'm going to be taking, let's do that example. If I'm going to be taking 3 books with me on a backpacking trip, and I've got 24 books to pick from, then it would be, I got 24, I'm choosing 3. And so there would be, again, damn it, it's the same number as the Domino's pizza. All right, let's see this one instead. How many different ways can you make a collection of 20 miniatures from a set of 1,000 different D&D miniatures? I was at the pool yesterday, and the lifeguard was talking about running Dungeons and Dragons. That was kind of cool. I was talking to him about that. So how many different ways? He apparently has just started playing D&D. He's a dungeon master. And I don't know, his game sounded pretty awesome. Like he had his friends going through a Ninja Turtles game, back in time, fighting dinosaurs and pirates and stuff. Sounds pretty amazing. So you got 1,000 different miniatures, and you're picking 20 of them. The order doesn't matter. They're either going to be in your display case or not. I don't know. I'd play that too. It sounds pretty fun. So in that case, it would be 1,000 choose 20, which is some large number. Okay. All right. So, which is a lot. Okay. So Blaise Pascal did a lot of cool things. He was a very smart guy indeed. He invented the mechanical calculator. So I don't know if you guys know this, but there's like a dozen or so of these left where it would actually do math in the 1600s. No electricity, no smartphones, but he had an arithmetic calculator. It's kind of cool. He wrote the Pinces, which he's pretty famous for, Pascal's wager. By the way, don't mispronounce or misread that word. It'll be embarrassing in your philosophy class. So, yeah, he's most famous for Pascal's wager, but he did other stuff as well. It's quite a good thing. Aren't pressure units named after him? Sure. He also said some pretty memeable stuff. Since we cannot know all there is to be known about anything, we ought to know a little bit about everything, which is something I kind of agree with. I think that you should at least have a passing knowledge of, like, all the important subjects in life, just so you're not missing something crucial. The sensitivity of men to small matters and their indifference to great ones indicates a strange inversion. So if you've ever seen people get upset about the stupidest stuff, that is what he's talking about there. People will get upset about trivial stuff and sort of don't care about the big picture. Finally, there is nothing so insupportable to man as to be in entire repose. That means at rest, without passion, occupation, amusement, or application. Then it is he feels his own nothingness, isolation, insignificance, dependent nature, powerlessness, emptiness. Immediately there issue from his soul ennui, sadness, chagrin, vexation, and despair. So don't just sit around your house playing PlayStation 5 all day. You know what I mean? If you can get one. Right? You gotta always have some task, some goal, some purpose you're working on. You know? Even if, you're not employed or whatever, like, that's your opportunity to, like, work on a project, right? You can, try and figure out how to do something. And, just work on stuff. It's really destructive, in my opinion, to the human soul to just have nothing to do, right? Like, some of my summers, when I was in K-12, were like that. I would just sit around the house and have nothing to do. I'd read books or whatever, but, after a while, like, it's just really painful, to just have nothing to do. There are other consoles, what he's saying. Yeah, jack of all trades. You don't have to necessarily be a jack of all trades. Like, you can be good. Like, I recommend being good at something, because that's how you get employed, or that's how you start your own business and do well at it. But, for example, if you start your own business, you should have at least passing knowledge of the law. Otherwise, your business is probably going to make a mistake, i.e. you are going to make a mistake at some point, and you get sued, or you lose a contract or something like that. You need to have at least a basic level of accounting and marketing and all these other things. And you will, as your business grows, you will hire people to do them for you, but you have to have at least a passing knowledge of how that stuff works. Otherwise, your accountant could defraud you for your money, or your marketing person could just sell you a bill of goods. They just completely lie to you because they're marketing people. That's what they do for a living. You know what I mean? So, it's important to be good at something, like really good. It's actually really good for the human soul to master a subject. And maybe computer science is a good thing to master. I don't know. But you need to like have a project you're working on or something, and you also need to have at least a passing knowledge of like all the major topics in life as well. So all human evil comes from a single cause: man's inability to sit still in a room. Okay, so anyhow, Blaise Pascal invented Pascal's triangle. And so this is a little mathematical device. You have ones down each of the edges of the triangle, and you fill it out one row at a time. Okay? So, jack of all trades versus specialization. Yes, I suggest both. Really, I suggest both jack of all trades and specialization. Seriously, in all seriousness, I'm not meaning here or anything. You need to be. It's really good to be good at something. Like, it's good for your spirit to know that you're good at something. And then on top of that, you need to know how to drive a car. You need to know how to plan a vacation. You have to know how to make a budget. You have to know how to you know what I mean. Like, there's a lot of things you have to have at least a basic level of knowledge in to succeed at life. And if you don't have them, you'll crash and burn. Like, if you don't have social skills, computer science majors, if you don't have social skills, it doesn't matter how smart you are, right? Like, one of my students back in the day was like, it doesn't matter, I don't need to have social skills. I am a genius, and so people will come to me to hire me. And didn't happen that way. Still working for his parents. So, Udemy, yeah, Arduino with C++ using OpenCV. Yeah, that's cool. Yeah, we do a little bit with OpenCV and CSI 45. Social skills, is that like Latin or something? It's funny. Yeah, social skills are actually really important, and it's a strange thing to say in a computer science class, but being able to like talk to people is kind of helpful. Knowing how to write an email without pissing them off, that's helpful. Yeah, so. Where's the civics chapter on social skills? Yeah, I wish, right? If you want to read a book on that kind of stuff, Kind of the all-time classic would be, where's my internet at? Where's my internet at? Come on. How to make friends and how to was it How to Make Friends and Influence People by, there you go. By Dale Carnegie, whose last name wasn't originally Carnegie. He changed it so it sounded like it was related to the business tycoon. Yeah. Great marketing, right? So this book is actually pretty good. Like it was written back in the 1920s, and so the examples are all like, well, Mrs. Wainscott went into the haberdasher and was trying to purchase a hat with a flower on it, and so the examples are all kind of like outdated, but the principles in it are actually really solid. So 79 cents on Kindle, $11 if you want a physical copy, and read it cover to cover. And I'm dead serious about that. I'm not going to grade you on it, but like if you want to be successful at life, understanding the principles in the book is like a really, really good thing. Super Friends, yeah. How to Win Friends and Influence People, yeah. So in all dead seriousness, like it's a really, really good book. Okay, so Blaise Pascal. So you got ones down one edge of the triangle, ones down the other. You fill it out a row at the time. And so what you do is for each spot on the row, each spot on the row is just the sum of the two people above it. Right, so this guy is 2 plus 1. This one is 6 is 3 plus 3. 4 is 1 plus 3. So as you can imagine, because you're adding ones, these go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this row goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this one, 3, 6, 10, 15, 21, 28, 36, 45. 3, 6, 10, 15, 21, 36, 45. The ones in the middle here look kind of weird. They're actually the combinatorics. They're actually 3 choose, 1 or whatever. 1, 2, 3, choose 1, it's 3. 4, choose 2. 1, 2, 3, 4, choose 2 is 6. So the Pascal's triangle actually is it's a chart holding the in choose k, and you can just fill it out as much as you want. And if you fill out 100 rows of it, then you'll have all the in choose k up to 100. And you just go down the thing. It starts at 0, not at 1. And you just go down, and then count across, and there you go. So it's indexed from 0. That's row 0. This is, if you do like 5, choose 0, 0, 1, 2, 3, 4, 5, choose 0 is 1. How many different ways can you make a committee of no people? 1. There's nobody on it. Done. Okay? So, pretty cool. When I was in middle school, we used to make these things and color them. Based on if they were like prime numbers or not prime numbers, like divisibility, like if they're divisible by this number, we'd color it royal blue, and if it's divisible by this number, we'd color it in green, and it'd actually make these really cool snowflake patterns and stuff like that. It's kind of neat. So, time for another break. So, let's go ahead and pause the recording here, and come back at 11:50. We'll do the last section of class then. Okay. Okay, start recording again. Yeah, okay. This will be the last bit for today. Okay. What is x plus y squared? Can anyone type that out in chat? See if you can do it before I can write it. Sit stand desk is a little awkward. Here we go. Oops, what happened here? Yep, just x plus y squared. Good. Alright. Alright, come race me. Can you do x plus y cubed? Okay. Come race me. X plus y to the 4th power. 2, 3. What's going on here? 2. Damn it. It's 3, 3, 1. Yeah, don't listen to me. 4, 6, 4xy cubed plus y to the fourth. Okay. Yeah, so if you weren't paying attention, what I'm doing is I'm writing down the coefficients off the Pascal's triangle. Okay, but I screwed up the beginning here, so my future ones got messed up as well. So yeah, so basically, if you were to write out, you know, what x plus y to the fifth power is, it's x fifth plus 5 x4 y1 plus 10x cubed y squared plus 10x squared y cubed plus 5xy fourth plus y to the fifth. And if you think that I'm doing that by actually doing the multiplication, I don't know why you would think that, because clearly I am not. So if you're ever trying to compute in algebra long expansions of polynomials, you can actually use Pascal's triangle to come up with the coefficients for it. So, does anyone want to take a crack at this one? What you do is you say at x equal to 3x, and you set y equal to 5y, or some y prime or something. And so then you just end up with x prime plus y prime to the 10th power. You do the whole expansion, and then you substitute back in. Okay. So x prime plus y prime to the 10th power would be x to the 10th, x prime to the 10th. It's going to be really hard to understand, huh? Plus 10x prime to the 9th y plus 45x prime to the 8th y prime squared dot 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 dot. And so what you do is you just substitute in the original thing there. So x is equal to 3x, so substitute that in. We put in 3x for x, take 3 to the 10th power, whatever number that is. It's like 3 to the 10th x plus 10 times 9 to the, or what is that? 3 to the, oh, damn it. 10 times, not 9, 10 times 3 to the 9th times 5x to the 9th y plus 45 times 3 to the 8th times 5 squared x8 y squared, so on and so forth. So what you do is, do you understand algebraic substitution? Like you substitute 5y in for y prime, you substitute in 3x for x prime, and then you just do the algebra on it. So if you needed to compute 3x plus 5y to the 10th power, you'd either do that by hand, which would be kind of hellish, or you can use Pascal's triangle, and then, you know, it'd take me a couple minutes, but I could probably work this out. Like, no problem, assuming I've had my coffee. Or we just did our break. You don't get another break. Sorry. Or you go into Wolfram Alpha and have that solve it for you. So, okay. So set builder notation. Yeah, I guess we can talk about this too. Then we'll call it. You need to get your next homework assignment anyway. So. Okay, you can make a set like this. Yeah, so you can just use English for sets. Like you can just be all, I'm going to make a set of all presidents born before 1800 or something like that, right? You just use English. It's fine. Or you can use something called set builder notation. And sometimes it's done with a vertical slash, sometimes it's done with a colon, because why would there be consistency in math? There's no consistency here. Huh. Okay. So for example, we're going to set a equal to all integers of the form 2n plus 1, where n is greater than or equal to 1. So this will have the number 3 in it, the number 5, the number 7. So it's basically all odd numbers bigger than 1. Okay. That's how I'd write this in English. So all elements of set z, which is integers, such that x squared is equal to x plus 2. So how many elements are in this set? How many elements are in set B? What do you think? How many elements? How many people in Z, in the class, the set of all integers? How many integers, if you square them, you will get that number plus 2? What's the size of B? Vertical slash B, vertical slash. What do you think? 2? There's 2 elements in that set? What are the two elements of that set? What is the size of B? Size is 1. Yeah. And that's something that let's look at the scores from the quiz last time. Quiz statistics. So pretty widespread on this one. So if we have foo bar baz and bar waz waz, what is the size of the union of them? And so the union is going to be foo bar baz, bar is already in there, waz waz. So there's 5 elements in there, which 9 people put down. That is in fact the set. It is, however, not what I'm asking for. I'm asking what is the size of the set. Don't ignore the vertical slash. Like I said last time, everyone does it. It's not a big deal. It's just how it is. So the size of the set is 5. Okay. If all integers in the universe is z, if A is all integers less than 100 and B is all integers greater than 50, what is the intersection? Okay. So the intersection of them is going to be up through 99. It's less than 100, so 100 is not in the set. And it's all integers greater than 50, so 50 is not in the set either. 51 is in the set. Elf null, no. Z, no. It's the intersection. So if it was a union, it would be Z. If it was the union of all numbers greater than 50 or less than 100, that's all integers, right? Because every integer is either greater than 50 or less than 100, right? 0 is less than 100, a million is greater than 50. So if it was the union, the answer would in fact be Z. That one is just the greater than, not greater than or equal to thing. And then Aleph null would be the size of, Aleph null is the size of Z. It's the cardinality of Z. So, yeah, we'll start there next time. Do I have a thing? No. Okay. Then let's talk about infinity real fast. Just finish with that. You got. Yep. Yeah, how does that, everyone? Myself included. All right. So here's a question. What is the size of Z? How big is that? How many integers are there? Countably infinite. Yes. Countably infinite. How do we write that? Yeah, we could write down aleph null, or we could write squiggly lined n null like that. So, cool. Are there more odd numbers than even numbers? Let's not do equal. Let's just say greater than. Are there more odd numbers than even numbers? I think. In Z. Z odds, Z evens, whatever. Probably not the most formal way of doing it, but the set of all integers such that they're of the form 2 times n is even, and of the form 2 times n plus 1 is odd, for all n greater than or equal to. Yeah. Would there be more odd numbers or even numbers? What do you think? Are there more odd numbers or even numbers? Wouldn't they be equal? I don't know. What do you think? If you start counting at 0, then, right, like half the time there's going to be more zeros than, like, evens than odds, right? It's infinite. Indeterminable? Nope. In fact, this is actually determinable, and the answer is they're equal. And the reason we know they're equal is because remember how we said you can determine if two sets have the same size if you can draw a one-to-one and onto correspondence with them, right? So if you can draw a one-to-one and onto correspondence between the natural numbers and the odd numbers, then these are both infinite sets, and they have the same size. And so the size of the odd numbers is actually aleph null, and the size of the even numbers is also aleph null, because you can draw one-to-one and onto correspondence using f of n equals what would it be 2n minus 1. So this is a one-to-one and onto function, right? So if you plug in 2 times 2 is 4, minus 1 is 3. So you can go backwards and forwards, and so this creates a one-to-one and onto correspondence between z, and this is z odd. Okay. And likewise, you can do the same thing with the even numbers, going the other way. And so they have the same size. Okay. So here's another question. Are there more odds or integers? Are there more integers or are there more odd integers? What do you think? Z is all integers. Odd is just 1, 3, 5, 7, 9, negative 1, negative 3, negative 5, so on and so forth. You think there's more odds than integers? That seems odd. You think there's more integers because there's even numbers, right? Double equals or single equals? As it turns out, there is the same number of odd numbers as there are integers. All right, same principle. There's the same number of even numbers as there are odd numbers. They're both all aleph null in size. Okay, there's the exact same number of odd numbers as there are integers. And the reason why we know this is, well, right here. If you can draw a one-to-one correspondence between every element in Z and every element in Z odd, they have the same number. You can't point to any place where there is more of one than the other, because for every element in Z odd, there's exactly one element in Z. For every element in Z, there's exactly one element in Z odd. They have the exact same cardinality, right? Just the same way that we can demonstrate that there's the same number of leopards and sheep. These are L's, believe it or not, S, 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 S. If you draw a 1-to-1 and onto correspondence between the leopards and the sheep, they have the same cardinality. Right? Like I said, this class leaps back and forth between the trivial, like, yes, there's 5 leopards and 5 sheep, and the what? Yes, there are as many odd numbers as there are integers. Okay? So, here's another question. Numbers where if they're divisible by 1 million, you get 0. Okay. So, what's bigger? The set of all numbers divisible by a million. That's a 1m right there. That means a million. So if you take the number, you divide it by a million, you get a remainder of 0. Right? Are there more numbers divisible by a million or integers? What do you think? See, as evens too, are they not counted? No. For every even number, there's exactly one odd number corresponding to them. Right? So for every number, there's exactly one number corresponding to them. And this stretches in the other direction for negatives as well, or you can alternate 1, -1, -1 or -3, 0, which corresponds to -1. Yeah, so you can alternate between positives and negatives if you want to include negative numbers, or you can just not worry about it. Because the natural numbers has the same cardinality as integers, so it doesn't make much of a difference. So what are there more of? 1 million, 2 million, 3 million, 4 million, 5 million, or integers? I'm going to assume, based on the pattern, that it is also equal. Yes, it is. Yes, it is, because we can create a 1-to-1 and onto correspondence between 1, 2, 3, 4 with 1 million, 2 million, 3 million, 4 million. Can anyone give me the algebraic function that translates between z over here and divisible by 1 million over here? Can anyone give me a function, f of x, that goes from this to this? Yeah. Is equal to 1 million times x. Yep. That's a 1-to-1 and onto function. If you graph it, looks like that or something, slope of a million. And so for every x, there is exactly 1 y. For every y, there's exactly 1 x. You remember that back from your middle school days. Yeah, believe it or not, you can use that to prove that two sets that are infinite in size, you can't count them exactly. They're called countable infinities. You can't really count them. They're called countable infinities because they sync up with the counting numbers, which we call n. So 1 corresponds to a million, 2 corresponds to 2 million, 3 corresponds to 3 million, and so on and so forth. For every integer, there is a number divisible by a million that corresponds to it. For every natural number, 1, 2, 3, 4, 5, there is exactly one element in the set. Therefore, these sets are exactly the same size. There are as many numbers divisible by a quadrillion as there are integers. What do you guys think? Kind of cool. Kind of cool. All right, let's do one more. So let's say, what is there more of? Floats between, floats being, 0.001 or whatever. No precision limit, right? Floats between 0 and 1. The size of that set, like what's in that set, like 0.6, 0.2, 0.01, right? You guys understand? The size of the numbers of floating point numbers between 0 and 1, is that greater than, less than, or equal to the size of the number of integers there are? The number of floating point numbers, numbers with decimals between 0 and 1, is that bigger than, smaller than, or equal to the number of integers? And the answer is equals. Nope, not equals. There are more of these. There are infinitely more numbers between 0 and 1 than there are integers. It is a greater infinity. It's not even countably infinite. It is uncountably infinite. There are far, far, far more numbers between 0 and 1 with decimals than there are integers. You know, some people call this aleph1. Squiggly line, squiggly line, squiggly line. But it gets a little bit weird because they're not really sure. So, there's more numbers between 0 and 1 than there are integers. It's a bigger infinity. There's, in fact, an entire hierarchy of infinities, of some infinities being bigger than other infinities. True story. I feel violated by the change of the pattern. And the reason for that is because you cannot draw a one-to-one and onto correspondence here. Like 1, 2, 3, 4, 5, dot, dot, dot. 1 can correspond to 0.1, let's say. 2 can correspond to 0.01. 3 can correspond to 0.001. 4 can correspond to 0.001. Oops, 0.001. 5 can correspond to 0.0001. Do you see that? You can never even get to 0.002. You can go infinitely down z, and all you keep corresponding with is yet one more 0 in front of the 1. You can never even get to a 2 in any decimal place. There's an infinite. There are more numbers between 0 and 0.0000001 in that range than there are integers. Can't ever get to 0.002. And so we're going to ask you, is what about the size of the numbers of the pattern 0.0? I don't know how to express this even, with x digits followed by a 1. Yeah, that's probably the same size as z, because you can have 1-to-1 and onto where you have a certain number of zeros. But yeah, I don't even know if the terminology even makes sense when you do that. But yeah, that's maybe the same size, because you can have 1 0 or 2 zeros or 3 zeros or 4 zeros. That's countably infinite. But if you're talking about the numbers between 0 and 0.01, the tiniest, get 500 zeros and a 1, that tiny, tiny little sliver of floating point numbers, there are more floating point numbers between 0 and 0.01 than there are integers. It's a much, much uncountably bigger infinite. Objection. All right, let's do one more. Just to hurt your brain a little more. Are there more rationals than integers? Do you remember what a rational is? 1/2, 1/3, 1/4, 2/3, 3/4, 7/1,000,000. Greater than, less than, or equal to. You're prepared for this? All right, let's see what you got. So it is the smallest points from 0 and 1 in floats that makes it different from integers. Yeah, because with an integer you got 0 and you got 1. With floats there's an infinite. Every range has an uncountably infinite number of numbers in there. All right. Looks like we got a consensus that there are more rationals than there are integers. We just introduced the notion of having different hierarchies of infinities. Survey says same size. How? Because like you think about it, like you can have 1/2 and 1/3 and 1/4, and it's the same thing, right? Like you just go all the way down, on the denominator side of things, and never get to a 2 in the numerator, right? Wrong. You're wrong. George Cantor, who was a genius, came up with this thing, something called Cantor Diagonalization, where, right, you've got z over here, 1, 2, 3, 4, 5, dot, 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 z, and he drew, these are the numerators, and these are the denominators. You got 1, and then you got 2 over 1, and 1 over 2, and 2 over 2, and 3 over 1, and 3 over 2, 1 over 3, 2 over 3, and 3 over 3. And so what he did was, rather than trying to run all the way down one of these things before he got to the next one, which you'd never finish because it's infinite, what he did was said, let's go this way. And if you do that, there's exactly one fraction for every element in Z. So 1 would correspond to this one, 2 would correspond to this one, 3 would correspond to this one, 4 would correspond to this one, 5 would correspond to this one, 6 would correspond to that one, and so on and so forth. You draw a zigzag pattern starting at the top left, which is the origin. You zigzag your way down. And if you do that, there's a one-to-one and onto correspondence between the rationals and the integers or natural numbers. And so it doesn't matter that you actually have a double infinite, right? Because you've got, essentially, you got numerator over denominator. That's, you know, infinite. And that's infinite. So it's like an infinite times an infinite. Turns out, it doesn't matter. It doesn't matter. It's still just Aleph null. So even though this is Aleph null and that's Aleph null, and you're kind of multiplying the combinations times each other, it doesn't matter. There are as many rationals as there are integers. That's annoying, but cool, I guess. Is there an Aleph null for imaginary numbers? Yeah, like for complex numbers, you can have an infinite, same thing. You use Cantor Diagonalization, where one of the row is the imaginary part and the columns are the real part, or vice versa, it doesn't matter. So for complex numbers, even if you have an integer coefficient, right, not decimal, not floats, right, if you have a you know, let's say an integer number for the complex part, integer number for the imaginary, or sorry, for the imaginary part, and an integer number for the real part, then you can use the exact same thing here to prove there are as many complex numbers as the size of all complex numbers. I don't know what the letter is off the top of my head. There are the same number of complex numbers as there are integers. What is this? What is the letter for it? I'm gonna guess C, but knowing math, it's probably gonna be like W or something like that. Oh, it is C, but a weird C. Okay, or C. Okay, I'll allow it. So, the size of paste. Ah, really? Just copy the hyperlink. All right. The size of weird-looking C. Okay. All right. Any questions about that? I'm sure you have tons of questions. Are they going to be on our? Are they going to be on our competency exam? Yep. If I change my C to times New Roman, it's complex infinity. 4 tries, right? Yeah. So that's the most fun part of set theory, is the size of infinite sets. And let me simplify all of it for you. If the numbers are integral, like I said, complex numbers. I don't know if I want to actually write this down. Because if you allow, you know, with int coefficients, right? With int coefficients, complex numbers is the size of z. If you had float coefficients, then it's like bigger than z. Okay, so it depends, right? Anytime you see like count the number of integers, that's going to be Aleph null. If you ever see count the number of floats, or some other way of putting it, the numbers between 0 and 1, that's going to be not Aleph null, bigger than Aleph null. Some people will say Aleph 1. It's not exactly that accurate, but rationals, right? A rational is an integer divided by an integer. It's still going to be Aleph null. That's your rule of thumb, okay? So if you see integer, 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 what's the size of this infinite set? Everything's integers. It's going to be Aleph null. That's the countable infinity. A countable infinity means you can pair it up with the counting numbers. 1, 2, 3, 4, 5. There's a 1-to-1 and onto correspondence between all the things in that set and the counting numbers. Uncountable infinities like floats, you can't. There's no way of pairing up the counting numbers with all the numbers in the set. You can't make a 1-to-1 and onto correspondence. So they're uncountably infinite. And there's some good links I could recommend. Number file, uncountable infinity, or something. What's that girl's name? Infinity's bigger than you think. What's V is her name, I think. What am I thinking of? Is that the same one? I don't know. V infinity. V hard. Yeah, that's one. Yeah, so I'll post these on Discord. It's I don't know. Her goal isn't to explode your brains like mine is, so maybe you'll enjoy it a little bit better. But yeah, the two sources of enjoyment I get from teaching this class are teaching modular division and teaching about Aleph null, because none of it makes any sense whatsoever. Like when you start, you're like, yeah, of course, there's more integers than there are odd numbers. Of course there are. Of course there's more integers than there are numbers divisible by a trillion. There's a trillion more of them. Nope. When it comes to things like infinity, all of those intuitions we've built up are wrong. They're just wrong. So, do you love teaching as much as recursion? I mean, really, in order to understand recursion, you have to understand recursion, right? So, 6 divided by 2 equals 7. Exactly. That's why the picture on Canvas is for Kearney explaining how modular division works. CSI 26 students. So I have to derive joy somehow from teaching, and this is part of it. Okay, so yeah, in general, the rule of thumb is the size of an infinite set is countably infinite, i.e. Aleph null, if you're dealing with integers. And if you're dealing with floats, it's going to be uncountably infinite, which is bigger than Aleph null. Okay, that's the nutshell. That Boromir pick was pretty epic too. Oh yeah. That was new for this year. I switched out the picture on that one this year. It is a strange fate that we should suffer so much fear and doubt over so small a thing, such a little thing, semicolon. Right? So they're all learning about the pain of missing a semicolon, or even putting an extra semicolon in, because a lot of CSI 40 students like putting a semicolon, else semicolon, if semicolon, truncating off whatever it is they were supposed to be doing. Because else semicolon means else do nothing. And so the thing they have indented over on the next line they think should only run on an else always runs. So, bigger than infinity. Yeah, bigger. Yeah. So like, there's probably some like infinity stone joke I can make there. So like, okay. So like the infinity stones that Thanos had are like Aleph null. And then like when Loki, I don't want to give a spoiler. In the Loki series, turns out there's an infinite number of infinity stones, but that's still countably infinite. So there's something more powerful than the infinity stones, and it's called the number of floats. I don't know. There's some sort of analogy you can make there. It's like the infinity stones are infinite, but like they're not They're not the biggest. Like, there's bigger than elephant. There's infinite timelines, and each timeline has a set of infinity stones, and yeah, I don't know. So you have an infinite number of infinities. That's still countably infinite. I don't know. Depends how you set it up, I guess. I don't know. But then you have the sacred time. I don't know. I don't know where I'm going with that. Anyway, the point is that there can be things more powerful than the infinity stones. So there's things bigger than Alephanal. And I'll post those those videos from Be Hard to Number file. They're kind of fun to go through. It will definitely expand your brain. I warned you at the beginning of the semester. There's going to be times when your brain will expand and press uncomfortably hard against the inside of your skull. So this is one of them. Infinite timelines and infinite possibilities. But in how many of them can you jet ski? That's the question. Okay, kind of like Python stuff, but with indentation. Yeah, really. Okay, so that's it for today. I'll put up a quiz on this. I'll put that on the... Yeah. There you go. That's ideally what you should be experiencing. maybe this one. hopefully this one. To achieve enlightenment. Okay, so that's it for you guys. I'll put up a quiz. I guess I'll give you a day off from programming. So we'll pick this back up on Thursday. If you didn't do the hash tables assignment, you have till next week to do it. Claim your last chance. It's a 20-point assignment, so you want to do it. All right. What time is the tutorial center open again? Currente, and you can probably answer that better than me. 9 a.m. Cool. All right. Open from 9 to 9. That's pretty good. Yeah, it's one of the nice things about our college is that we have a really nice tutorial center that will assist you in your computer science endeavors. At my college, we had help for calculus and writing, and that was it. If you wanted help with computer science, you had to go to your professor's office hours, or if you had a TA, the TA's office hours. But there wasn't just like a tutorial center you just drop in on, stuff like that. So, yeah, it's a really nice resource we have. Hopefully some of you learned that it's okay to ask for help. There will be times during the semester where things will be confusing to you, and you need to get clarification or need help on it, and that's normal. Get into the habit of asking for clarification or asking for help on your homework assignments, because that's how real life is. I Google things all the time. All right, so 2 to 6 online. All right, cool. All right, I will see you guys on Thursday. Hope you have a great day. Stuff your brain cells back into your head. You'll be fine. All right, take it easy, guys.